Now we'll start the special roots of an equation x to the power n minus 1 equals to 0. So here the definition is the roots of the equation x to the power n minus 1 equals to 0, which is not a root of the equation x to the power m minus 1 equals to 0, where m is any integer less than n, is set to be special root or primitive root of the equation x to the power n minus 1. So here I will write the first recall. The recall is the definition of special roots. So special roots of the equation to the power n minus 1 equals to 0. So the definition is basically a root of the equation x to the power n minus 1 equals to 0, which is not a root of the equation x to the power m minus 1 equals to 0, where m is any integer less than n. Is set to special roots is said to be special roots of the equation x to the power n minus 1 equals to 0. So I'll give you one example. So as for example, I'm writing here the equation of the form x to the power n minus 1 equals to 0, and we'll find out the special roots. So now here I will take the value of n. So this will be few examples of the special roots. Now if you take say n equals to 1, so that means the equation of the form x minus 1 equals to 0. And obviously, okay, first we will write the roots, then we will come to the special roots. So roots is 1, and here the root of the equation x minus 1, which is not of the root x to the power m, where m is integer less than n. So obviously here the special root will be 1. Now we come to the second. If we put n equals to 2, the equation will be x square minus 1 equals to 0. So what are the roots? 1 and minus 1 are the roots. But 1 is not a special roots. This is not a special roots because 1 is the root of the lower degree equation x minus 1 equals to 0. That's why 1 is not. So the special roots is only minus 1. Now if you think about x cube minus 1 equals to 0, what are the roots? The roots is 1 omega square, where omega is the imaginary cube root of unity. So 1 is the root of x square minus 1 as well as x minus 1. That means lower degree equation of same type. So 1 is not a special root. So omega square are the special roots. Omega square. Now we come to the equation for n equals to 4. It will be x to the power 4 minus 1 equals to 0. So what are the roots? 1 minus 1 minus I. But okay, 1 is the root of x minus 1, x square minus 1, x cube minus 1. That's the lower degree equation. So this is not a special root. Minus 1 is also root of x square minus 1, where 2 is less than 4. So this is not a special root. The special roots are here, I and minus I. In that way, we will continue what are the special roots. For n equals to 5, x to the power 5 minus 1 equals to 0. And this is your exercise. You will write the roots here and you will write what are the special roots. So special roots is basically one kind of root of the equation x to the power n minus 1 equals to 0, which is not a root of the lower degree equation x to the power m minus 1 equals to 0. That root is considered as the special roots. Okay. So now we'll come to the one important theorem for special roots, but before that we'll think about the roots of the equation x to the power n minus 1 equals to 0. So now the recall is so first we'll find out the roots of the equation x to the power n minus 1 equals to 0. Okay, then we will think about the special roots. So if we write x to the power n minus 1 equals to 0, that means we are trying to find out the nth root of unity. Okay, so what are the nth root of unity? Or you can say nth root of unity. Okay, so that means we can write here. So x to the power n equals to 1. That means x to the power n equals to cos 0 plus I sin 0. Because equation a degree is n. The degree of the equation n of a is n. So it has n roots and no more. That means the root may be real or complex, but the root is exactly n in numbers. So that means we can write here x equals to cos 0 plus 2k pi is a periodic function plus I sin 0 plus 2k pi whole to the power 1 by n. Now what is k? We need nth root, n number of absolute roots, so where k equals to 0, 1 to up to n minus 1. So that we can write cos 2k pi by n plus I sin 2k pi by n. What is k? Where k equals to 0, 1 to up to n minus 1. Here we apply this De Moivre's theorem and we will find out the roots. So that we can write cos 2k by n 2 pi by n plus I sin 2 pi by n whole to the power k again by De Moivre's theorem. Okay, so by De Moivre's theorem. So that we can write e to the power 2 pi by n whole to the power k, where k equals to 0, 1 to up to n minus 1. So e to the power 2k pi by n I. What is k? K equals to 0 to n minus 1. Or we can say from here the complete list of roots of x to the power n minus 1 equals to 0. This is equals to 1 alpha square dot alpha to the power n minus n. What is alpha? Where alpha equals to e to the power 2 pi by n whole to the power I. So this is our alpha. That means it is basically cos 2 pi by n plus I sin 2 pi by n. So this is the complete list of root of the equation. So here the complete list of the root of the equation x to the power n minus 1 equals to 0. So this is 1 alpha square, alpha to the power n minus 1. What is alpha? Cos 2 pi by n plus I sin 2 pi by n. Okay. Now the question is that we can write e to the power 2 pi by ni by Euler's theorem. So this is the complete list of roots. But we need to find out which roots are special root among the complete list of roots. Okay. We have n roots of the equation x to the power n minus 1 equals to 0. But we need to think about the special root of x to the power n minus 1 equals to 0. So this is the speciality of the concept. So now we'll apply one important recall or theorem from which you will decide which roots are special roots and which are not. So the theorem is the special roots of the equation x to the power n minus 1 equals to 0 are cos 2 pi by n plus I sin 2 pi by n. 2 pi r by n. What is r? Where r is a positive integer, where r is a positive integer less than n and prime to n. Less than n and prime to n. So we'll write the set of special roots in that way. So next we call special roots of x to the power n minus 1 equals to 0. This is, we consider is be the set of all special roots of the equation x to the power n minus 1 equals to 0. So if we consider this set is S, so S contains the roots of the form cos 2 pi r by n plus I sin 2 pi r by n. That from what is r? Here r is a positive integer, r belongs to natural number, r is less than n, and GCD of Rn, this is equals to 1. So that means we can write here cos 2 pi by n plus I sin 2 pi by n whole to the power r. Then r belongs to such that r belongs to natural number, r is less than n, and GCD of Rn equals to 1. That we can write e to the power 2 pi by n I whole to the power r, where r belongs to natural number, r less than n, and GCD of Rn equals to 1. That we can write alpha to the power r such that r belongs to natural number, r less than n, and GCD of Rn equals to 1. And what is alpha? Alpha is e to the power 2 pi by n I. That means cos 2 pi by n plus I sin 2 pi by n. So these are the set of all special roots of the equation x to the power n minus 1 equals to 0. Okay, so we are not doing any kind of proof here, but okay, so this theorem we need to recall, statement we need to recall. So the special roots of the equation x to the power n minus 1 is 0, that is of the form is, so where r is the positive integer less than n and prime to n. Now we'll come to the note. If n is a prime number, the first note, if n is a prime number, if n is a prime number, that means n equals to 2, 3 or 5 or 7. Every root, that means n equals to 2, 3, 5, 7, 11, 13 and so on. Then every root of the equation x to the power n minus 1 equals to 0, except 1 is a special roots. Okay, so this corollary is important. Why? Because you know the special root set is, so what is the set of special roots? So just I will give a hint. Is such as the set of all special roots of x to the power n minus 1 equals to 0. Let and n equals to p, a prime number. So then what will be s? S will be alpha to the power r, so that r is less than n, r is less than p, r belongs to natural number, and GCD of Rn equals to 1. The question is, what is alpha? Where alpha equals to cos 2 pi by p plus I sin 2 pi by p is prime. So that means here it will be alpha square, alpha cube dot alpha to the power p minus 1. That will be the possibility. Since r less than p, this is prime, and GCD of r and p, this will be p, this is 1. So as p is prime, so that means what are the possibility of r? The possibility r will be 1, 2, 3 up to p minus 1. So that means except 1, all are the special roots. So here, this is a corollary 1 under note 1. Corollary under, so how many special roots exist? So cardinality of the set S will be p minus 1. Okay. So the question is the number of special roots of the equation x to the power p minus 1 equals to 0, where p is prime, is option A 1, option B p minus 1, option C p, and option D R, where 1 greater than or less than p minus 1. So here option B is correct. All other options are false. This kind of question may be asked from special root section. Now we come to the next important note. So what will be the number of special roots of the equation? Now we'll come to the question. The number of special roots of the equation x to the power n minus 1 equals to 0, where n is a natural number. So that we need to give the answer. So what are the special roots? So special roots of the equation that we know, x to the power n minus 1 equals to 0, that set equals to alpha to the power r. What is r? R is a natural number, r less than n, and GCD of r and n equals to 1. And what is alpha? Alpha equals to cos 2 pi by n plus I sin 2 pi by n. Okay. So that means it completely depends on, it is same as. So if we think about the number of special roots, so that will be the cardinality of this set. This is exactly same as the cardinality of r belongs to natural number such that r less than n, and GCD of Rn equals to 1. Okay, and that cardinality is basically phi n. Phi n means number of positive integers less than n and prime to n, and this happens for n greater than 2. Okay, so here the answer is number of special roots of the equation x to the power n minus 1 equals to 0. This is, the answer is phi n. So what is phi n? Phi n basically the number of positive integers less than n and prime to n. So what is phi? Phi is basically Euler phi function. This is Euler phi function. Now we come to the next important recall under special roots of the equation x to the power n minus 1 equals to 0. The recall is basically, if alpha be a special root, if alpha be a special root of the equation x to the power n minus of the equation x to the power n minus 1 equals to 0, then 1 by alpha is also a special root of it. Okay, so this is another important recall. If alpha be a special root, then 1 by alpha must be a special root. But how we will prove? If alpha is special roots, then 1 by alpha is also special root. How to prove it? So now we'll come to the proof and we'll prove it easily. So now the special roots. First we try to think about special roots of the equation. X to the power n minus 1 equals to 0, that are cos 2r pi by n plus I sin 2r pi by n. What is n? Where r is less than n, where r is natural number, r is less than n, and r is prime to n. So that means GCD of Rn equals to 1. So these are the special roots. Now, okay, we are thinking let alpha equals to cos 2r pi by n, cos 2r pi by n plus I sin 2r pi by n. Okay, where r is a particular value, this is less than n, and GCD of Rn equals to 1. If we take alpha is like this, then alpha is a special root of the equation x to the power n minus 1 equals to 0. Now the important case is here. Since r is less than n and prime to n, and GCD of Rn equals to 1, that implies n minus r is also less than n, and GCD of n minus r, and this is also 1. Okay, and hence if we put in position of r n minus r, hence cos 2 n minus r pi by n plus I sin 2 n minus r pi by n, this is also a special root, of x to the power n minus 1 equals to 0. Because n minus r less than n and GCD of n minus r n 1. This is a condition to be a special root. So that means, that implies cos 2r pi by n minus I sin 2r pi by n. This is a special root of x to the power n minus 1 equals to 0. Okay, because since cos 2 n minus r pi by n plus I sin 2 n minus r pi by n, that is exactly equal to cos 2 r pi by n, that will be minus I sin 2 r pi by n. That is a simple trigonometric calculation, and this implies 1 by cos 2 r pi by n plus I sin 2 r pi by n. This is a special root of x to the power n minus 1 equals to 0. That is basically our alpha. So 1 by alpha is a special root of x to the power n minus 1 equals to 0. Hence, the proof is complete. So proved. So what we proved, if alpha is a special root of the equation x to the power n minus 1, then 1 by alpha is also special root. Okay, so here we will note the one important recall. We know if alpha is a root, then 1 by alpha must be a root if the equation is a reciprocal equation. That we have done previous concept. So that will come to one important note, or you can say the recall. The note is basically the special root of the equation x to the power n minus 1 equals to 0. This is equals to the roots of the reciprocal equation. The roots of the reciprocal equation of degree phi n. Okay. So that means the special root of the equation x square minus 1, that will be the roots of the reciprocal equation of degree phi 2. That means 1. Okay. Now we come to the next important recall or theorem. If alpha be a special root of the equation, if alpha be a special roots of the equation x to the power n minus 1 equals to 0, then 1 alpha square alpha to the power n minus 1 is a complete list of distinct roots of the equation x to the power n minus 1 equals to 0. So this theorem is helpful. So what the theorem says, you find a special root of x to the power n minus 1 equals to 0. From that information, we just do alpha to the power 0, alpha to the power 1, alpha to the power n minus 1. That means 1 alpha square alpha to the power n. This complete list, that will be the complete list of roots of x to the power n minus 1 equals to 0. It is so simple. Just you need to find out one special roots. So find one special roots, and then from that root, say alpha, from that root you can set up the complete list of distinct roots. So how to find out the complete list of distinct roots of an equation? So just you think about one special root, and then you will think about the power alpha to the power 0, alpha to the power alpha to the power n minus n. You will get all the distinct roots. So this is very tricky and very obvious. Now we come to another important recall. Let n equals to PQ, where P and Q are prime to each other, where P and Q are prime to each other. If alpha be special roots, if alpha be a special roots of the equation x to the power p minus 1 equals to 0, and beta be a special root of the equation x to the power q minus 1 equals to 0, then alpha beta, then the product of this special root is also a special root of x to the power pq, that means x to the power n minus 1 equals to 0. So now the question is how to prove. This theorem is important in graduation course or any kind of competitive examination. The question is how to prove. How to prove this kind of theorem. So what is exactly given? What are given? Given n equals to PQ, P into Q, where PQ are prime to each other, that means GCD of PQ equals to 1. The first information. The second information, alpha is a special root of x to the power p minus 1 equals to 0. The third information, beta is a special root of x to the power q minus 1 equals to 0. What we have to prove? We have to prove that alpha beta is a special root of x to the power n minus 1 equals to 0. That we have to prove. Now we come to the proof part. We have written till now what is exactly given and what we have to do. Since alpha is a special root of x to the power p minus 1 equals to 0 and beta is a special root of x to the power q minus 1 equals to 0. So we have alpha to the power p minus 1 equals to 0 and beta to the power q minus 1 equals to 0. So that means here alpha to the power p equals to 1, beta to the power q equals to 1. Okay. Now we come to alpha beta is a root. First we think about alpha beta is the root of x to the power n minus 1. Then alpha beta whole to the power n, it satisfies the equation. So alpha beta whole to the power n, that we can write alpha beta to the power pq, since n equals to pq. That we can write alpha to the power p whole to the power q, beta to the power q whole to the power p. So by 1, alpha to the power p is 1. So 1 to the power q, 1 to the power p. So this is basically 1. So that implies alpha beta whole to the power n minus 1 equals to 0. and that implies alpha beta is a root of the equation, is a root of the equation x to the power n minus 1 equals to 0, because alpha beta satisfied the equation. Now we are thinking about special roots. So how alpha beta will be the special roots? Okay. So that means we will say alpha beta is not a root of alpha beta x to the power k minus 1, where k is less than n is an integer. So we are assuming that let alpha beta whole to the power k equals to 1. So then alpha to the power k equals to beta to the power minus k. From that we can write alpha to the power qk, this is equals to beta to the power minus qk, and that will be beta to the power q whole to the power minus k, that will be 1. Since beta to the power q equals to 1. Again, since, so here we have done alpha to the power qk, this is basically 1. Again, since alpha to the power p is 1 and alpha to the power qk, this is equals to 1, and alpha is a special root, so qk must be greater than p. Since alpha is a special root of x to the power p minus 1 equals to 0. So we let qk equals to sp plus r by division algorithm, where 0 less than equals to r less than p, and alpha to the power so now we know alpha to the power qk equals to 1, so that means alpha to the power sp plus r equals to 1. That implies alpha to the power r equals to 1. Since alpha to the power p equals to 1, that implies alpha to the power sp equals to 1. So alpha to the power r equals to 1 and alpha is special root, so r must be 0. Therefore, that implies p divides qk since r equals to 0. Again, GCD of pq equals to 1. Since GCD of pq equals to 1 and p divides qk, so from that we can write p divides k. And similarly, in the same way, if we start alpha to the power pk in position of q, if we take p, in similar way you can prove q divides k. It's 2. So from 1 and 2 we can write, therefore from 1 and 2 we can write pq divides k, since GCD of pq equals to 1. Why? As p divides k, q divides k, GCD of pq is 1, so pq divides k. So that means n divides k. So therefore, alpha beta whole to the power k equals to 1, and that implies n divides k. And hence we can write alpha beta is a special roots of the equation x to the power n minus 1 equals to 0. So now we'll solve some problem. The problem is question paper. So this problem is given or taken from MAPA book. So what is the problem? Find the special root. Problem number 1, very important. Find the special roots of the equation x to the power 12 minus 1 equals to 0. So how we will prove? We will prove based on the theorem. Solution: the special roots of the equation x to the power 12 minus 1 equals to 0 are cos 2r pi by 12 plus I sin 2r pi by 12. The question is, what is r? Where r is less than 12, r is natural number, and GCD of r at 12 are basically 1. So therefore, what is r? R is less than n and prime to n. That means r is less than 12 or prime to 12. So we will think of number of integers less than 12 and prime to 12. These are 1, 5, 7 and 11. So thus special roots are thus the special roots are cos 2r pi by 12 plus I sin 2r pi by 12, where r equals to 1, 5, 7, 11. This we can write cos 2r pi by 12 plus minus I sin 2r pi 12, where r equals to 1, 5. So that is the special root, sir. If we put r equals to 1, cos pi by 6 plus minus I sin pi by 6. If we put r equals to 5 here, so that will be cos 5 pi by 6 plus minus I sin 5 pi by 6. That is root 3 plus minus I by 2, comma minus 3 minus root 3 plus minus I by 2. So these are the special roots of the equation. We can solve this problem in the other way, but okay, we'll do the next problem. Problem number 2. So that the special root of the equation x to the power 9 minus 1 equals to 0 are the roots of the equation x to the power 6 plus x cube plus 1 equals to 0. So how to solve this kind of problem? Since 1 and 3 are the only divisors of 9, since 1 and 3 are only divisors of 9 and less than 9, so the non-special roots of the equation x to the power 9 minus 1 equals to 0 are given by the roots x minus 1 equals to 0 and x cube minus 1 equals to 0. So here we will write a recall. That recall is important, the supportive recall for this paragraph. So what is the supportive recall? So recall is a non-special root of the equation x to the power n minus 1 equals to 0 is a root of x to the power m minus 1 equals to 0 for some m less than n. So now we'll continue the problem. So now we'll calculate the LCM. Now the LCM, least common multiple of x minus 1 and x cube minus 1. This is x cube minus 1. Next we'll divide the equation x to the power n minus 1 by the LCM, x cube minus 1. And that will be x6 plus x cube plus 1. So therefore, the special roots are the roots of the equation are the roots of the equation x to the power 6 plus x cube plus 1 equals to 0. Now we'll go to one important problem. This is question number 3, but this question given in exercise. Let alpha be special root. Let alpha be a special root of the equation x to the power 8 minus 1 equals to 0. Then prove that alpha plus 2 multiple alpha square plus 2 alpha to the power 7 plus 2, that will be 85. And next 2 1 plus 3 alpha plus 5 alpha square dot 15 alpha to the power 7. This will be 16 by alpha minus 1. So now we'll come to the solution. Since alpha is a special root, special root of the equation x to the power 8 minus 1 equals to 0. So the complete list of roots of the equation, the complete list of distinct roots of the equation are 1 alpha square dot alpha to the power 8 minus 1, that means 7. So we have x to the power 8 minus 1. This is equals to, because it is a complete list, x minus 1, x minus alpha square, x minus alpha to the power 7. This is an identity. So now we'll put x equals to 2. So putting x equals to 2 on the both sides, what we get? We get x equals to minus 2 on the both sides, because we need alpha plus 2 or alpha plus 3. So that will be better if we put x equals to, that will be right way, put x equals to minus 2. So minus 2 whole to the power 8 minus 1. That will be minus 2 minus 1, minus 2 minus alpha, minus 2 minus alpha square, minus 2 minus alpha to the power 7. And that will be 3 into 2 plus alpha, 2 plus alpha square, 2 plus alpha to the power 7. This is equals to 2 to the power 8 minus 1. So that means here alpha plus 2 into alpha square plus 2, alpha to the power 7 plus 2. So 2 to the power 8 minus 1 by 3. So that will be 85. So what is the answer? Thus the value of alpha plus 2 into alpha square plus 2, alpha to the power 7 plus 2 is 85. Now we will come to the next problem, but okay, next problem given as an exercise for you. So this is basically self-in exercise. You will